Yes, thank you. So this is collaborative work with Møller from Aarhus University and Michael Pradel. So where does our approach fit in with existing work? So we are kind of in the sweet spot between existing UI testing techniques, concurrency bug detection, and test generation. What we are looking at is a collaborative web application where we have several clients that connect to the same document. So imagine something like Google Docs or Microsoft Word Online or other similar applications, and the edits made by the clients are performed concurrently, and there's a notion of eventual consistency that eventually all the edits get synchronized to all clients and they see the same state. The complexities of analyzing such an application come from the fact that we have different browsers. They may have bugs in the browser-side implementation with JavaScript, which is kind of an ugly language to write in. Then we have concurrent interactions, which add to the complexity and the fact that it's distributed and messages take some time to get delivered. So let's look at an example of a concurrency bug in Google Docs that our analysis finds. So we have two clients that both have the text foo written in bold font in them as the initial state, and then we perform concurrent changes to that, where in client 1 we write an additional text bar, and in client 2 we delete the existing text. After this, we see the following synchronization of the concurrent changes, where on client 1 we have the bold text bar, and on client 2 we have the non-bold normal font bar. And this doesn't synchronize. Eventually, it stays different on both clients. And it's bad enough that both clients see a different view of what is supposed to be the same document and the same state, but also when you continue to edit in a document that has been broken like this, you will also run into this pop-up box, which is a complete crash in Google Docs. You have to reload the page and you might miss some of the work you've been doing. So we want to develop an analysis that finds these kinds of bugs, and the challenges for developing our analysis are first the huge space of client actions that can possibly be performed. We have the state space of the low-level interleavings between those client actions based on the client-to-server communication protocol. And there's the complex system that may, based on the clients and whatever is implemented on the server side, that has various components that need to be looked at. And there's the challenge of defining a usable test oracle to find concurrency bugs. So for the huge state spaces, we cannot explore them fully, so we need a practical way to limit this state space to make our analysis applicable. And for the complex system, we need a way to abstract it to focus on something that allows us to find bugs. So we present our approach that is called Simian, and it's the technique for analyzing these collaborative web applications that is automatic. So the user doesn't need to specify the complex interactions between several clients themselves. It is scalable because it treats the entire system component, the server component, as a black box. And it is systematic because it does a bounded exploration of all potential conflicts. And it is precise, so we don't report any false positives. Before we look at how we detect violations of the correctness of collaborative web editors, let's look at how correctness is usually implemented in them. So the operational transformation approach is one possible way to implement a collaborative editor. It's a non-blocking concurrency control algorithm, and it's the one we found most implemented in in real-life applications. So in this, we have two input states, sigma 1 and sigma 2, and we have concurrently performed operations, operation 1 and operation 2 on those clients. And then in order to synchronize those, there's a transformation function so that the operation 2 gets transformed to be performed on state sigma 1, that we get an output state sigma 1 prime. And what this transformation function ensures is that if we transform all operations into execute then on each client, that if the input states sigma 1 and sigma 2 were equivalent, then the output states have to also be equivalent. So the correctness property used by operational transformation contains a precedence property and a convergence property. And what Simian targets to find bugs, violations of, is this convergence property, where the output states are not equivalent. We use a more high-level concept of an action for our implementation. So it's a logical step triggered by the user, and it can consist of multiple implementation level operations as used by operational transformation. So this is something like insert the text A, or mark the current line and make it bold, or delete the last character, like pressing backspace. Our analysis has two phases. So as an input, we get this list of actions, and then in the sequential phase, we calculate a list of potential conflicts. And then in the parallel phase, we use two clients to test those potential conflicts, whether they can actually lead to an inconsistency where the output of the two clients is different. What we need for our approach is first the concept of a state. So we need to reason about how to compare different states. First, we use a pixel-based state abstraction for that. So if you want to tell if two states are equivalent, we just take screenshots of both clients and then see whether all the pixels match between them. That's how we tell equivalent states. And then how do we tell inconsistent states? We again take the screenshots of both of them and then compare the pixels. So in this case, we see one of the A characters is in italic and the other one is not. So that's an inconsistent state because the pixels are different. In the sequential phase, we first pre-select interactions that modify the same data concurrently. And we want to maximize the potential for synchronization problems that we test in the second phase. So this is the idea of the sequential phase, to run a pre-selection experiments on a single client, and then after you've pre-selected some interesting interactions, test those on two clients. And this reduces the number of interactions that need to be tested in parallel. What we do in this sequential phase is we look at an action tree like this one. So the nodes of the tree are the states of the single client that we use in the sequential phase. So we start in the root node with an empty state, and then we have the actions on the edges. So from the root node that is empty, we perform the type character A action, and then we come into a state where the character A exists, and then we can take the bold action to get to a state where the bold character A exists. What we do is we execute all single client interactions that traverse from the root to one of the leaf nodes, and we bound the depth of the tree with the variable parameter k. We perform all of these actions for all leaf nodes and record all the state differences that happen when we perform these actions. Then we check what are the equivalent states, because there's some action sequences that are actually equivalent, like the action type A, and delete nothing from the empty state and then type another character A, so that's equivalent. And we don't want to look at those two states as two different states, so we merge all the information that we have for them, And then we want to look at potential conflicts in those states, which we define as when two actions modify the same data. So in this case, the actions bold and delete both modify the single existing character A of the state, and we count that as a potential conflict to feed into the second phase. So then for each state, numbers of states in the equivalence class, we merge all the lists of potential conflict pairs so that we have for a state that only contains a single non-bold character A, we have the pair bold and delete as one of the potential conflicts. To tell whether two actions are potentially conflicting, we again use our pixel-based state abstraction. So from the single input non-bold character A, we have the one change to bold and one change where the character is deleted. We look for the affected areas with pixel differencing and check whether those affected areas overlap. And when they overlap, we consider those two actions to be potentially conflicting. Then, after we have collected these potential conflicts, we enter the parallel phase where we check whether executing this interaction with the two actions that we called a potential conflict in parallel actually leads to an inconsistent output. Now we add a second client to our analysis. So with the set of potential conflicts here in the top, we have first the input state, that is on the left you have a single character A that is not bold, and on the right you have the example where the character is bold, and then you have the two actions that should be executed in parallel. And then for the multi-client interaction, we first have a sequential step where we try to reach that state. So with one of the possible options, given that with the equivalence class there can be multiple prefixes that lead to the same state. And once we've reached that state, we have this parallel suffix of the multi-client interaction where both are executed concurrently. In order to abstract away from the state space that can happen due to the possible low-level interleavings, we don't look at different interleavings, but we let it non-deterministically choose one of the possible interleavings that this can happen. So let's look at the interaction on the right as an example. So we first start off with a client, with a single client in the sequential step where we have a single character A, and then we make it bold with the bold action, and then we add the second client to go into the parallel step, and then from there we can perform the concurrent action. So we type an additional character A and press delete, and we get this unsynchronized state, and then the application can have one of two possible outcomes. One is the correct synchronization where both states show a bold character A, and the other possible outcome is the incorrect outcome where one of the A's is not bold anymore. And this is selected non-deterministically. After we've done this, so for each multi-client interaction that we have created, there is a rating we have whether it produces a consistent state or an inconsistent state. And this is reported to the user as the result of the simian approach. Which interactions lead to inconsistencies? So we have implemented this using Selenium, and we have a Selenium server where we control two Firefox applications to let them automatically perform these actions for us. And what I want to show here is we have the artifact available, and this is open source on my GitHub, where you can download Simian and try to apply it to your own applications. So for our evaluation, we've looked at 3 applications. We have Google Docs, and we have FirePad, and we have OwnCloud Documents. For those 3 apps, we use the same set of 10 actions to analyze them as the input. And those are common actions such as typing characters and pressing buttons like pressing backspace or tab, or applying formatting like bold or italic. So that's our set of actions that we give to the analysis. And then we show what inconsistencies Simian reports. So for different exploration depths k of the sequential phase, we get different outputs. So for Google Docs, we find 37 inconsistencies, so 37 multi-client interactions that can lead to an inconsistency. And for OwnCloud, we find over 130 different inconsistencies. So what this shows is the usefulness of Simian based on this rather simple heuristic of how we detect whether there has been a concurrency bug. And let's look at some more examples of these kinds of concurrency bugs that we found. So in OwnCloud, we have the interaction where first we set the font face to Verdana, and then concurrently we type characters A and B. What we get as an output is this one, where one of the characters B on one of the clients does not have the correct font formatting, so the font on both clients is actually different. And Simian detected that the pixels are different. That is why we get this as a report. Then another bug in Google Docs. So first we set the font size to 18. Then we type the character B. And then concurrently we perform the actions pressing tab and pressing space. And that gets a very interesting outcome. So we have these screenshots. So what you first notice is we only typed a single character B, but actually we get two of them here. So the act of pressing tab and space at the same time has gotten us a second B that wasn't there before. And this is actually something that Simian could not detect on its own because it's wrong on both clients. But the reason why this gets flagged by Simian is because also this space character in between has a different font size on both clients. And what this means is that even though we have a more limited oracle to find concurrency bugs, we also find with this oracle more serious bugs where data appears out of nowhere with that oracle. So the output of Simian is non-deterministic because it just executes each multi-client interaction once without care for different interleaving. So here we compare how big the influence of the non-determinism is. We have two runs, R1 and R2 of Simian using the same inputs. So for all applications, we see that between the two runs, the number of reported inconsistencies is very similar. And we see that for Google Docs and Firepad, between the two runs, about half of the inconsistencies are actually different inconsistencies that we did not find in the other run. Whereas for OwnCloud, we find that the inconsistencies that get reported are very stable. Then, briefly about the performance of Simian, we find one inconsistency every 9 minutes. And we spent about 27 to 47% in the sequential phase of the application. And the usefulness of this sequential phase is that if we drop it and just try to synthesize all possible multi-client interactions of a length, then the entire approach slows down by about 10 times. So this is why we use the sequential phase to make the analysis practicable in the first place. In conclusion, we have presented the analysis of collaborative web applications that is automatic, it's scalable, it's systematic and precise. We've shown the novel two-phase analysis of concurrent systems and our black box reasoning about them, and we have the implementation of that system available. For future work, we would like to suggest one is a explicit exploration of the non-determinism that we experience, and The idea is also to cluster inconsistencies that we found by the root causes, by looking at the source code and finding out which number of those many inconsistencies that we found correspond to the same bug in the source code of those applications. Okay, that's it. Thank you.
So the pixel approach, that was very, very cool. And I'm wondering if you have different systems, different screen methods.
Yeah, it actually does. So we have the same Firefox that we control with Selenium, where we make sure that it has the same resolution. And even on the exact same system with the same resolution, there's some problem based on the native font rendering that some shadows might be very slightly different between two times taking the screenshot of the same application. So there's some, we cut off some very tiny pixel areas and we only look at larger connected areas that we check as state differences. Yeah?
Yeah. Within just a few years ago, there was a lot of research on bounded model checking. This paper very much reminds me of some of those projects. Most of this model checking was done for hardware, not software. But there was a lot of work done in optimizing these types of searches. So I'm wondering if you've looked at any of those papers.
So model checking requires a more white box approach of looking exactly at, like if you do dynamic partial order reduction, for example, you would need to look at the individual HTTP messages that get sent between the client and the server, and it would require a lot more reverse engineering between those messages that contain information about the state you're not interested in, like nonces. So with this black box approach, it's more practicable to apply on applications like Google Docs, which we didn't even have the source code of the server for. We were still able to analyze with that, which is a different approach than software model checking. So one of these future works that I have here that would go more into that direction of model checking.
Sequential phase generation, does it happen once for your entire test suite? Because somehow my intuition was that that it can be different runs.
Yeah.
So how do you work around this situation?
Yeah, so of course you have to run it independently for each application. So if you test Google Docs, you will get a different output of the sequential phase compared to OnCloud, obviously. And then for those two different runs which I've shown, that was with this same sequential phase. So using different sequential phases, we assume that it is deterministic. That is an assumption, but there can also, of course, when we don't have the server source code, we don't actually know whether its actions are actually that deterministic or not. So this is something further that is worthy of looking at in future work.
So it was very interesting to see some real life in Google Cloud. So you have some example on font popular. So have you found anything related to removal of text instead of introducing more text or changing the font?
So all bugs that we have are either formatting differences or appearance of new characters that you didn't type in. We've also had some bugs in FirePad where additional overlays appear that are not part of the document but part of the UI that become inconsistent. But we haven't found any. So where data loss can happen is once you've reached such an inconsistent state and there's two different formattings on both clients, then when you continue to edit that concurrently, you will easily run into a crash and then you can lose your data because it hasn't synchronized with Google Docs yet, and then you will have to reload the page and lose what you have typed in.
Thank you very